Alright, so far we've been working with right angle triangles. I think it's about time to expand our range of triangles that we are looking at in this trigonometry course. So this is some right angle triangle here. Remember, if it has side r and angle theta, then I can say that this side over here is r sine theta. And this is r cos theta. So this observation is really helpful and really something that you want to get used to. You're going to use this a lot when you study mechanics as well, just sort of projecting the angles under the right angle components, making use of sine and cosine to do that. Just by the definition, sine and cosine are just ratios of the sides of a triangle. So this is a really good way to deal with algebra, and you can use this to prove a lot of things, as you're about to see. So one thing that we will look at when we're looking at general triangles, so we'll try and keep this as general as possible. Let's have the sides B and A with angles. Angles capital B and capital A. So the first general rule when it comes to triangles, is that basically we want to have this relation here. So B over sine B. So A over sine A is B over sine B. So what is this rule? It's known as the sine rule. It's true for all triangles. Comes up in a variety of contexts. You can see that I can also just I could have wrote this down instead. This is the same thing. But I'm actually now comparing the ratio of the sine of an angle to its opposite sides, right? Notice if I put another, like, angle C and C, you can just see but that this would be true as well. I could just write another equal sign in there, right? So this rule can be written in a variety of ways, but let's undo all that. Don't really care about that. All you really need to know is that this is the sine rule and how we're going to use it. In the next video, I'll provide some examples of just walking you through different cases where it might come up and use. But for now, let's explore why this is true. Okay, so what is the proof of this? What is the justification for writing such a thing? Well, it's actually really easy when the angle B is acute. And, there's the foot of the perpendicular of this triangle. Let's call this side H. And remember, up here, you can take the hypotenuse of a right angle triangle. You can write the other two sides in terms of the hypotenuse and an angle. Well, that's exactly what we're going to do here. We see that H is equal to, if you look at the left, I'm just going to extrapolate that hypotenuse onto that side. So I get B sine A. But looking at the right triangle, the one on the right, I can also extrapolate that hypotenuse A, and I see that it must be A sine B as well. Okay? So now we can forget about H and just compare these two. I see that B over sine B is A over sine A. I get exactly what I wanted to get when angle B is acute. So that proves it for half of the infinite amount of triangles there are. Then we consider the other case. Okay, and we see that this angle here, B, okay, now it's obtuse, sure. Fill in everything, A and A. Well, again, this is just exactly the same argument, right? Let's kill the height of the triangle H. You can see that, the only difference is we're going to use one of those relations that we had from before. So first of all, extrapolate this hypotenuse. I get that H is equal to sine. So H is equal to B sine A. And then I'm going to extrapolate this hypotenuse. What angle is this? It's 180 minus B. So H is also equal to A sine 180 minus B. Okay, which means that b over sine 180 minus b is equal to a over sine a. But of course, remember, sine 180 minus b, that's just sine of b. Okay, we covered that identity in the last video. So again, this this relationship holds for, well, all triangles now. We've kind of justified why that's true. So it's an interesting rule. It's relating the ratio of sides to the ratio of sides to the ratio sides of the ratio of sides. I'm gonna end the video on the clock chime. Peace.